Okay, so now what we're going to do, and all this is, by the way, this is corresponding to the second half of chapter 3 in your text, so that hopefully get a chance to take a look at this later on. Let's go ahead and proceed. So we don't really have a clicker question, but I want you guys to think about a question. We don't have clickers tonight, but ask yourself, well, let me ask you this question. Suppose we had a bowling ball and a feather, okay, suspended at the same time, and then we release them at the same exact time. Which one do you think is going to hit the ground first if we could ignore air resistance? Bowling ball, feather, or were they both at the same time? So I'll give you a second to think about it, and if you want, you could even type in your response into the chat room. That'd be kind of cool to see what you think. Don't worry, I'm not going to share your results with everybody. I just want to see what you think. Okay, I got one vote for same. Anybody else? Bowling ball. Tie. Both at the same time. Okay, cool. Hi, what do you think? Maybe Hi is not back yet. Okay. All right, good. So what do you think? Which one will hit the floor first? Ty responds, yep. Give me an answer, Ty. What do you think? Okay. Take a few more seconds and then take your response in. All right, I'm going to go ahead and get going. So now, we talked about Claudius Ptolemy and his work. Again, just dominates for 1,500 years. And what I alluded to at the beginning in the previous discussion was the fact that this was actually held in great esteem by a lot of institutions, namely the dominant religious institution of medieval Europe was, of course, the Holy Roman Catholic Church. And there was an astronomer, really probably the first modern day scientist, who took ideas and tested them through observation and experimentation. So, I've mentioned Tycho Brahe being the first to use observation. Galileo actually was able to use not just observations of the heavens, but also experimentation with related objects here on Earth. And his results contradicted the church's teachings, and it got him ultimately into a fair amount of hot water with the government at the time. At the time, the church was the state, so the Catholic Church ultimately placed him under house arrest, and he recanted just before he died, but I think it was really too late for him to get out of the house. And in 1992, the Catholic Church did make a formal apology. So, the Catholic Church accepts the findings of Galileo. I'm not sure why it took until 1992, but there you go. It's often been claimed that he was the first person to ever point a telescope to the heavens. That's not really true. It actually was really a testament to his ability at self-promotion. He really knew how to write and sell a good book and tell a story and kind of leave the impression that he was the first to ever take a spyglass and point it to the heavens. What he did do, though, was make some very careful and detailed observations, and then use those observations he studied those observations to arrive at some conclusions as to how the heavens operated. One of the deeply held beliefs of the church's teachings was that despite Copernicus, and despite Tycho Brahe, and despite Kepler, they still held on to the belief that the Earth was at the center of the cosmos, and that everything surrounded the cosmos, and moreover, everything in the heavens was placed there by God, and therefore they must be perfect and immutable. So here we have an image of, this is an actual photograph of two of Galileo's first telescopes. They're extremely crude and primitive, even by the standard of telescope that you can purchase at a Costco. I mean, seriously, what you pick up in a Costco is toy telescopes, way better than what Galileo had back in the day. He built these by hand. They were pretty simple instruments. He was a very patient observer, and he nevertheless managed to make some very remarkable discoveries. One of the first discoveries that he made was looking at the moon. We look up at the moon, you can see that there are some different colors on the moon, but despite the different shadings, in some areas might appear to be lighter in color than others. The church and indeed the state still held that the moon was a perfect sphere. It was this beautiful translucent sphere, this orb, perfectly flat, placed in the heavens. Well, what Galileo discovered was that by inspecting the moon at different phases, he noticed that the edge of the shadow, a region called the terminator on the moon, was not a perfect straight line. What he discovered instead was that there were little jags, and some parts of the shadow would be just a little bit longer than the others, and other parts of the shadow would seem a little bit shorter than the others, and it wasn't a straight line, it was a squiggly line. And what he was able to deduce from this was that the moon must have higher regions on its surface and lower regions on its surface. And those lower regions on its surface would have a deeper shadow, but the higher regions in the surface would extend the shadow further. And he realized that the moon was not this perfect sphere, that it was in fact an imperfect, a jagged, rough-edged, rough-surfaced sphere. Another observation that Galileo made was he noticed that Venus went through phases like the moon, or similar to the moon. So on the right, you see Galileo's drawings. On the left, of course, there is a modern-day photograph. And what he was able to work out was that the planet Venus must be orbiting not the Earth, but the Sun. This is the only way you can have Venus undergo phases. So when Venus is on the opposite side, or nearly the opposite side of the Sun, because you cannot look at the Sun to see Venus, but the closer Venus appeared to get to the Sun as it was going behind the Sun, the more full Venus would appear. And then the closer Venus came toward Earth in its orbit around the Sun, the more crescent Venus would appear. And then it would eventually become new Venus. We wouldn't see it because now Venus is lost in the glare of the sunlight. And then you'd see a crescent Venus again, a waxing crescent Venus, and then a half of a Venus, and then a increasingly gibbous Venus, and then it would go behind the sun, then it would come back out the other side as a gibbous Venus, and then work its way back to a half illuminated Venus, and then to a crescent Venus before becoming a new Venus. Not only does Venus undergo these phase changes, but Venus's apparent size in his eyepiece decreased as Venus went from crescent down to full, or nearly full. This told Galileo that the only way for this to happen was if Venus orbits the sun and it's full because Venus is farthest away from Earth. In other words, it's on the opposite side of the sun. None of these observations are possible in a geocentric universe. If Venus goes around the Earth, you cannot have Venus undergoing phase changes like this. So that was another strong piece of evidence that Galileo uncovered that went against what were then the church's teachings. Another observation that he made was of Jupiter. And this is an excerpt from Galileo's own notebook. And at the center of each of these drawings, this is Jupiter as seen on different dates. And he noticed that Jupiter had these attendant stars, and that these attendant stars would change their position on either side of Jupiter from one night to the next, and sometimes you see 4 of these stars, sometimes just 3, sometimes even just 2. He decided that these stars were not really the stars of the heavens of the celestial sphere, that these must instead be satellites orbiting Jupiter. And so Galileo was funded by Cosimo il de' Medici, who was the Grand Duke of Tuscany. And so in honor of his patron, he named them the Medician stars after Medici and his 3 brothers. Astronomers later would change the names of these satellites of Jupiter and we refer to them to this day as the Galilean moons. These are 4 of Jupiter's. These are 4 Jupiter's moons. Indeed, we'll learn later on, these are Jupiter's largest moons. But what was fascinating and pivotal about this observation, this set of observations, was that the church was teaching that everything in the heavens revolves around the earth. And Galileo was able to demonstrate with these observations that, well, maybe Jupiter's orbiting the earth, maybe Jupiter's orbiting the sun. But regardless, even if Jupiter is orbiting the earth, these Medicean stars, as he called them, were orbiting Jupiter. They were not orbiting Earth. In other words, not everything in the heavens orbited Earth. There was at least something out there. There was at least one example he found where stars must be traveling around Jupiter, coming in front and then going behind, coming in front and going behind, thus tracing out the apparent side, some on one side, some on the other, from night to night to night. So this defied the church's teachings. Another idea that was held by Aristotle, going all the way back to his day and taught by the church, was that objects must fall at a speed according to their weight. In other words, if you drop the bowling ball and the feather, and even if air did not cause resistance, the bowling ball must always strike the ground first. In fact, let's forget the feather. Maybe the air is going to do something. Let's say a heavy rock and a lightweight rock. So both pretty solid objects. If you drop them, the heavy rock must strike the ground first. That is, of course, obvious. Galileo went atop the Leaning Tower of Pisa. It wasn't leaning quite as much back in those days, but it was starting to lean a little bit. And he conducted some experiments. He said, let's test this idea out. So he grabbed, some rocks of the, different weights. One was a bit heavier than the other. And he dropped them. He had an assistant stand at the bottom, and he'd ask him to call out when they hit. And he would just repeat this experiment over and over again. And as near as Galileo could make out, they were hitting the ground at just about the same time. That was not what was being taught. And just as a kind of a nice, cool proof of concept, even though we didn't need to wait until the Apollo mission, I'd like to show you a little video of an experiment that was conducted on the surface of the moon during Apollo 15 in 1972. So I'm going to go ahead and let me go ahead and everybody hear that okay? See that okay? Good. Yes. Thumbs up. Okay, great. Thanks. So you're seeing this is the footage from 1972. We didn't exactly have high definition TV back in those days. And the fact that it was being transmitted from the moon meant that the transmission was all the more ratty. But just watch this. Check this out. He's referring to an experiment used to measure something called the solar wind. We'll talk about that later. Okay, hopefully you all caught that. I know the image wasn't so great, but you could see the hammer and the feather as depicted in the painting. Both fell at the same rate and struck the ground at the same time. So why doesn't that happen here on Earth? And as you probably have guessed by now, air resistance. You know, the air pushes up against the hammer and the feather, but because the hammer is so much heavier, it overcomes that resistance much quicker. The feather is much more susceptible to the air resistance, and so it floats down a little bit slower. But that was just a very cool way to absolutely prove Galileo's observations were correct when you just go where there is no air, such as the moon, the surface of the moon. So, let's see. So what happened was, oh yeah, I'm sorry. So taking the story back from Galileo to Kepler, briefly, he discovered, as I mentioned before, these three laws of motion. He understood that they were happening. He didn't understand exactly why. You know, we have this third law, which is going to work great for planets orbiting the sun, but this Kepler's law, this idea that the square of the period is equal to the cube of the semi-major axis, only seems to work for planets around the sun. It does not work for planets, for moons orbiting Jupiter, for example. And so Galileo couldn't fit this planetary law, this law of planetary motion, into his observations of Jupiter. He couldn't predict when the moons of Jupiter would be visible again using that law. And he lacked the mathematical skills in order to figure out a way to take Kepler's work and kind of generalize it for not just planets moving around the sun, but also for moons orbiting planets. So we're going to delve into the solution to that question in a bit more detail, but the person that cracked it, that finally cracked it, was this man. This is Sir Isaac Newton. He was doing his thing in the late 1600s to early 1700s, and he is truly one of history's greatest geniuses. He actually discovered physical laws of motion and gravity. He used mathematics that not only could explain what was observed, but could, most importantly, predict future observations. And they could then be tested, and they could be timed, and they could be scheduled, and you can look and you can see that the phenomena that he was able to use his laws to predict did in fact occur when predicted. A famous example is of Halley's comet. Sir Edmund Halley approached Isaac Newton when he learned of Isaac Newton's work and asked him to predict for him, please, when will this comet that he suspected was a recurring event would come around again. We'll talk about Comet Halley in a little, perhaps in the next week. But what was truly incredible about Newton's work is that he realized that the laws of gravitation and motion that play out here on Earth are also true in the heavens. Indeed, these laws are universal, literally universal. They must apply and work everywhere. So now what I want to do is talk about Isaac Newton's three laws of motion. And then we're going to apply those laws of motion that he discovered to gravity next week. But the first law is this idea of something called the law of inertia. It goes like this. If you were to just take a object on your table, okay, and maybe it's something kind of lightweight, you know, maybe your glass case or something like that, and you know, if you just slid it across the table, it's going to move a certain distance, and then it's just going to come to a stop. I mean, we all know this from our everyday experience. If you want something to continue to move, you have to keep pushing on it. Okay, and it was widely believed that objects left to their own devices are always going to remain at rest. They're always going to want to return to a stopped state, that it requires some external effort to keep things moving. What Isaac Newton learned was that actually an object has a tendency to want to remain at rest, but once that tendency is overcome and it is set into motion, it will then remain in continuous motion, and it will have the tendency to stay that way and keep going and going and going and going until something else, some other force interacts with it to change its tendency to remain in motion and eventually bring it to a tendency to remain still. So an object's tendency to remain in motion or always remain still is a phenomena called inertia. Okay, it's really just a measure of an object's, basically it's a measure of of the difficulty in which it is to change an object's tendency to remain at rest or tendency to remain in uniform constant motion. So if you have a spacecraft in space and you fire the rocket, you get it moving, and then you cut off the rocket, the spacecraft will not slow down. It will keep going and going, and it will maintain that speed and in that direction. This will be constant, and we call something that has a constant speed moving in a constant direction, we call that a value called velocity. So Newton's first law, simply stated, says that an object will remain at rest or continue moving along a straight line at a constant speed, i.e. it's going to have a constant velocity, until acted upon by an external force. So it's going to take a force, an external force, okay? Your glass's case is not going to just pick up and move on its own. It needs some external force to get it going, and then once it gets going through space, it needs another external force to either change its direction or to bring it to a stop. Okay, so forces play a role in getting things to get them moving, and to get them to change direction, and to get them to slow down and eventually get them to stop. Okay, so a tendency for an object to maintain its velocity, even if that velocity is zero and it's not going anywhere, is known as the object's inertia. So let's talk now about motion. Okay, I mentioned two quantities, speed versus velocity. By the way, this is the Tesla Model S, the world's first all-electric luxury sedan. And my birthday is in October, if anybody's watching. Anyway, if we have our Model S cruising along in a straight line, we can consider speed as a change in position. Okay, so we started here, and then sometime later we ended up over here. So we have a change in position over time. Okay, that is the definition of speed. You notice that I'm not specifying what direction we're heading in. I'm just simply saying that this Tesla is moving at 34 meters per second. So we call this quantity, we give this a special name, we call this a scalar quantity. In other words, it measures what's known as magnitude, and magnitude is simply another way of saying an amount of something. So its speed, its amount of, its rate of change in position over time is 34 meters per second. If, on the other hand, you say, well, we're driving at 34 meters per second due east, now I've defined a very specific direction, and I've defined a speed. If you have a speed and direction, you have velocity. Velocity, instead of being a scalar quantity, is what's called a vector quantity. Vectors simply describe an object's magnitude, or a quantity's magnitude, and its direction. So if you have the magnitude only, you have a scalar quantity. If you have magnitude and direction, you have a vector quantity. I only bring this up because we're going to be playing around a little bit with this idea of vectors and things being directed in a certain direction. It's pretty important to our understanding of motion. So if you're confused, feel free to ask a question, but we'll just keep it going. So if velocity, think about this, if velocity is speed and direction, that means that if we change either the speed or the direction, we have a new phenomena known as acceleration. So acceleration is a change in velocity over time. And I've written it out here just to kind of break it down a little bit. I'm using bold-faced A to indicate that A means acceleration, and the fact that it's bold-faced, it means it's a vector. In other words, it's directed in a very specific direction. So the vector quantity A is the vector quantity velocity divided by time. Notice that time is a scalar quantity. There is no direction of time unless you count from past to future, but there really is no direction of time. We're going to learn about some other scalar quantities such as mass. Mass is a measure of the amount of something, and it doesn't matter what direction that mass is moving in, the mass is the same, so mass is always scalar. Anyway, notice that if we are hitting the accelerator in our car, we've gone from one velocity to a new velocity, right? We've changed our velocity over some time. That's acceleration. Also notice that, you notice that I said we change our velocity. I didn't say we always increase our velocity. What if you hit the brakes? Does that change your velocity? Yeah, it does. Guess what? You're accelerating. Except that whereas before, when you hit the accelerator, your acceleration is directed in the direction of your motion. If you hit the brakes, the acceleration is now directed opposite your direction of motion. Okay, so think about that. Keep in mind this concept of direction playing a role. By the way, if we maintain our speed of 30, well, coming around this curve, maybe we're doing just, maybe we're just doing like 5 or 6 meters per second. But anyway, if we turn our steering wheel, we've changed our direction. Even though we're maintaining our speed, guess what? We've changed our velocity. We've accelerated. Every time you turn the steering wheel in your car, you're accelerating. Every time you change direction, walking down the hall, you're accelerating. Even if you are traveling at the same rate of speed, you are accelerating because you are changing your direction. So keep that in mind. It's a change. Acceleration is defined as a change of speed or direction over time. Now, when you actually kind of do the analysis on the units, I'm going to use meters per second. These are kind of like standard scientific units. The velocity is measured in meters per second in some direction. I'm omitting the direction there. And we're changing the velocity over time. So that's meters per second. And if you remember some of your algebra, if you divide something by something, that's the same thing as just taking both values and sending them both into the denominator. And since we have seconds times seconds, that's the same thing as saying seconds squared, so it's meters per second squared. Okay. Let me see if I've lost anybody. Okay, cool. All right, great. So now we can talk about Newton's third law of motion. Remember when I said, I'm sorry, second law of motion, excuse me. Remember when I said that an object's inertia is a measure of its tendency to remain at rest. And once it gets going, it's a tendency to remain in constant velocity, now that we know what that is, right? Constant motion in the same direction, unless a force interacts with it. That force has to be directed in some specific direction. So force is a vector quantity. It's always going to be directed in some direction. That means if you want to get something moving, you've got to give it a force, and you've got to give it a force directed in some specific direction. So if something changes its either direction or speed, you get this quantity called acceleration. And the object is going to have some amount of mass. We can regard inertia now as mass as a measure of inertia, right? Mass is another way of saying the object's tendency to remain at rest or remain in motion. That's mass. So an object's acceleration, as it turns out, is going to be equal to the net force. In other words, the force that you're pushing or pulling or yanking or whatever direction you're directing that force in, divided by the object's mass. Therefore, the acceleration is always going to be in the same direction as the force. So what I'm showing you here is an image from one of the earliest servicing missions to the Hubble Space Telescope. This is astronaut Catherine Thornton. She's holding in her hand a telephone booth-sized instrument that's going to be installed on board the Hubble Space Telescope, which is off to the left of your image. And this instrument you know, it has a lot of mass, okay? In fact, if it were placed on a scale on Earth, I think it weighs something like, it weighs about the same as a small car, you know, about 1.5 tons, 2 tons. It's a pretty heavy instrument. You know, therefore it has a lot of mass. So even though it's in space, and we're going to talk later about this concept of weightlessness in space, but you're probably already familiar with the idea that, you know, when you're in space, things don't have any weight. Everything just sort of floats around. She still had to get a really good grip on this and really give it a good force, a good push in order to accelerate it, to get it moving. And then had to really kind of hold on to it in order to keep it from floating away and just moving away from her. Really hang on to it. Why? Because this object has a lot of mass. So if you take the force, divide it by its mass, you get the resulting acceleration, or as Newton phrased it, the force is equal to an object's mass times the acceleration that it develops. Okay, are there any questions? Click in the chat window here. Cool. Finally, Newton has a third law of motion, and it's his famous third law. You may have heard of this one. Some people have expressed this as for every action, there's an equal and opposite reaction. It's not so much for every action. It's really for every force, there's an equal and opposite reaction force. And so what do we mean by equal and opposite? Well, we mean two things. We mean equal in magnitude. Okay, so equal in the amount, but directly opposite in its direction. So in the case of a rocket or the space shuttle, we have, let's see, 1, 2, 3, 5 engines, okay, working here. And they're each doing it. The space shuttle's engines and the solid rocket boosters are doing this by 2 different chemical reactions, but the net result is the same. You take this mass, the rocket fuel, okay, and you throw it out, you accelerate it out the back. All right, so that means you're giving the rocket, you're applying a force to the rocket fuel. You're throwing it out the back. The rocket fuel responds by exerting an equal force on the shuttle, but it's directed in the opposite direction. And as a result, the shuttle accelerates upward as the exhaust, as the fuel is being accelerated downward, okay? So the forces equal one another. So it's this idea, you take this mass, you take this fuel, you throw it out the back end, all right? The fuel throws you forward as a result, and it accelerates you. Now, there's another example of Newton's third law that's maybe not as exciting, but guess what? You're doing it right now. You're sitting in your chair, and the chair, you're pushing down on the chair with a force. That force, we're going to learn later on, has a special name. It's called your weight. But you're pushing down on the chair with your force. The chair is pushing back up on you with an equal and opposite force. It's a force that is exactly equal to your weight, but it's directed in the opposite direction, and that's a good thing. Otherwise, you just blend right through the chair and blend right into the earth and fall right through down to the very center of the earth if this third law of motion did not exist and was not acting upon you. So these are Newton's 3 laws of motion, and when we get together again to talk about this, we're going to learn that these 3 laws paint a very important picture of this idea of gravity and planetary motion. So with that, are there any questions before we close out tonight? I'm just looking in the chat window. Okay, well, I appreciate you hanging in with me tonight. This was actually a lot easier for me to record this for an audience as opposed to just talking to the camera. I will get this posted somewhere for everybody not here watching at home. Please, well, by this point, you hopefully would have reviewed this. And in lab on Wednesday night, we're going to take a look at some of Kepler's observations, and we're going to calculate the orbit of Mars. Thank you very much, and I'll see you Wednesday night, weather permitting, who knows. Take care, bye.